This is the final lecture in our series from Chapter 12, and this one's going to be a little bit longer, so hang in there. This time we're going to talk about nuclear energy and the environment. So first of all, what is nuclear energy? Well, nuclear energy is the energy from an atomic nucleus. And there are two ways that we can access nuclear energy. We can either access it through fission, a fission reaction, or by a fusion reaction. And these two are very important to keep straight. One of them, fission, is the one we're using right now. Fusion is a reaction that people hope to harness in the future, but right now it's a little bit too dangerous and unpredictable for us to manage. Now, in a fission reaction, a heavy nucleus, like uranium-235, is split apart into smaller nuclei, and then a large amount of energy is released. So splitting apart the nucleus of the atom creates different products. So at the end of the process, we no longer have uranium-235. We have a variety of different other elements, because as uranium-235 is split, it releases protons and neutrons, which changes the chemical element that we actually have. Now, in a fusion reaction, we take a very light nucleus like hydrogen, which just has one proton in its nucleus, and smash it into another hydrogen at such a high speed and with so much force that the two nuclei fuse together and make a helium nucleus. And so far, fusion reactions only occur readily in stars. We have figured out how to make them happen briefly in laboratories, but not on a wide scale, and not anything that we can currently use for energy generation. So if you watch old sci-fi movies, they'll talk about the scientist who has discovered cold fusion. Now that would be the idea that we could smash two hydrogen atoms together at such a high speed and temperature that they fuse, but all of this takes place in a cold chamber or something less than 14,000 degrees Celsius, which is currently what's required. So we haven't figured out fusion yet. Fission, however, is going to be the topic of this lecture. So a little bit more about fission. Uranium is our primary fuel for fission. It is a radioactive element, and it occurs in two radioactive forms in nature, uranium-235 and uranium-238. Now, for physical and chemical reasons beyond me, only uranium-235 is fissionable, which means that it's the only form of the element that we can use to create nuclear energy. Now, the drawback is that uranium-235 only occurs 0.7% of the time in nature. So 99.3% of the uranium we find in nature is uranium-238. So we have to go through this process called enrichment to increase the concentration of uranium-235 in the sample so that we can actually use it for nuclear fission. Now, what a nuclear reactor does is it allows this fission process to take place at a controlled rate. So that means that we determine how fast and how hot the temperature inside the reactor becomes. And this enriched uranium is about 3% uranium-235 and 97% uranium-238. Now, it's pretty easy to build a nuclear reactor. The hard part is getting your hand on the enriched uranium. So when they talk about nuclear technology being sold to someone else, it's really actually the process of enrichment that is the tricky part. The actual reactor itself is fairly simple, and so how to enrich uranium is one of those secrets that the United States is trying to keep fairly closely guarded, so that the technology does not fall into the hands of terrorists. So, quick quiz question for you. Which uranium is fissionable? Is it uranium-235 or uranium-238? And it's going to be important you remember this because it's easy to get the two mixed up. And the correct answer, if you haven't picked it already, the correct answer is A, uranium-235. So I hate doing the factoids you just have to memorize, but that's one of the ones you have to memorize. All right, so here's the basics of a nuclear reaction. The large blue dots represent uranium-235, and the neutrons, if you look there in the I'm just going to use my mouse and see if this can work. So here is a neutron. Sorry, here's a uranium-235 nucleus, and here is a neutron that is flying towards the uranium-235. Now, this is what begins the reaction. All it takes to start the reaction is one well-placed neutron. And once that uranium-235 nucleus breaks apart, it releases additional neutrons here. Plus the red is all of the heat that's released. So all these additional neutrons then go on to fly out and hit other uranium nuclei around them, which then release more neutrons, which hit more nuclei. Now, in an uncontrolled manner, this nuclear reaction results in the atomic bomb. But in a controlled manner, we can prevent the reaction from proceeding too quickly, and we can slow the rate of reaction by absorbing these neutrons, these excess neutrons, and we can make sure that it proceeds slowly enough that we can generate and control the amount of heat that's produced. So here's what a nuclear reactor looks like. And this is where the reaction actually takes place. So in here, we have uranium-235, and we have carbon or some kinds of control rods made of some kind of material that will absorb neutrons. So what happens is the reaction gets started, and then if it's proceeding too quickly, they sort of insert the control rods to absorb some of those neutrons and slow it down. If they need the reaction to go more quickly, they'll pull the control rods out part of the way, and that will speed the reaction up. Now, this reactor is very well protected. So we've got this reactor in the center, we have a primary concrete shield around it, and the only two gaps in that shield are the places where the coolant comes in and then the places where the hot coolant leaves. So this circuit here is completely self-contained. This fluid that passes through the reactor never touches any other fluid, in theory. So the cold coolant enters the reactor chamber, becomes warmed up by the heat from the nuclear reaction, and then passes on out and heats up, passes through another chamber where it's inside a pipe, but the heat is able to diffuse. And as the heat diffuses, the coolant cools off, and then the liquid in this other circuit here becomes warmed up. So this is water, and as the cold water passes over the warm coolant, the cold water warms up, absorbs the heat, turns into steam, and then the steam is used to turn a turbine. So this should sound very familiar. This is basically taking heat from a reaction and then using it to boil water, turn a turbine. Now the heat from this reaction is just produced by a nuclear reaction rather than burning coal or oil. Now as the turbine turns, it spins the generator, and the generator, as you remember, is coils of wire with magnets, and the movement of those two in relation to each other creates a flow of electricity. Now the way that we get this hot steam that's turning the turbine cooled off again is we have another circuit where we bring cold water in from an outside source and then use it to absorb the leftover heat, the residual heat from the steam, and that condenses the steam back to liquid water before it moves on. And then the final output, we get two outputs from this, actually three. We get electricity generated, and then we have hot water that's coming back out, so warmer water coming back out of our system, being discharged into a local lake or river or stream. And then finally we have all of our spent nuclear fuel that has to be disposed of. And in case I forget to mention it later, this warm water that's being discharged, that warm water is one of the environmental drawbacks to nuclear energy, because water that's warmer than about 70 degrees or so does not hold as much oxygen as colder water. So warmer water actually makes it more difficult for fish and other animals to breathe because there isn't enough oxygen available in the water, and then it can also mess up the balance of the ecosystem because warmer water is easier for bacteria to grow in, certain kinds, and warmer water may be outside the temperature tolerance for some of the native fish. So the fact that we are, I mean, it seems kind of benign, we're just going to heat up some water and then we're going to, bring in cold water, put out warm water, no big deal. It actually does affect the local ecosystems. So that's one thing that nuclear power plants have to take into account. So hopefully you guys can go back over this description in your book if you have any further questions. All right, so quiz question to make sure you understand that diagram there. Electricity is generated from nuclear reactions by A, capturing the movement of alpha particles as they bombard a turbine, B, using gamma rays to create an electromagnetic field, C, fusing two uranium atoms together to generate heat and turn a turbine, or D, capturing heat from the fission of uranium to boil water and turn a turbine. So I know it's a lot to take in. Go ahead and pause your recording if you need to think about it. And the correct answer is D, capturing heat from the fission of uranium to boil water and turn a turbine. If you have questions, just scroll back a little bit, review that figure of the nuclear power plant, and then move forward. All right, so we've got some new technology we're going to talk about, new nuclear technology, before we get into the discussion of advantages and disadvantages. So most reactors that are in operation right now are called burner reactors, which means that they consume more nuclear fuel than they produce. So at the end of the day, with a typical uranium-235 reactor, we produce a bunch of waste at the end that then has to be disposed of. Scientists are working on some new technology called breeder reactors. Now, breeder reactors actually produce more fissionable material the longer they operate. So breeder reactors, if you fuel a breeder reactor, your end product is more fuel, which means that you could, in theory, make this process sustainable. Now, breeder reactors are capable of using thorium, which is a different atom, different element, or they can actually make uranium-235 fissionable. So this is very helpful if we want to look at nuclear fuel as a long-term option for our energy resources. And this would actually, if we use only breeder reactors, this would actually make nuclear technology renewable technology, which some people think is pretty cool. Now there's another kind of reactor that's just been developed, and it's a smaller reactor. It's called a pebble bed reactor. And this is because the reactor, instead of using rods, it actually uses little pebbles. And let's start by explaining what the pebble looks like. So inside every pebble, there are a bunch of tiny uranium particles that are coated in graphite. So the graphite actually serves to absorb neutrons, which will slow down the reaction, and it also protects the uranium from exposure to water, which would prevent any water from carrying radioactive material away from this reactor. So the way that a pebble bed reactor works is it's exactly the same kind of system. For the most part, we've got a helium fluid that carries the heat away from the reactor. We boil water, turn a turbine, spin a generator. The difference is here that each of these pebbles can be controlled very carefully, whether how many are inside the reactor core, and then as soon as they're done, they can be dropped out, and we can control it just by dropping one pebble out, adding one pebble in. So it makes it much easier to control, and it also makes it easier to dispose of these things. So the uranium oxide coated in graphite is the fuel, like I said. And so as far as advantages, there's the safety. You can make sure that there's never too much fuel in the reactor, so you can actually control how many pebbles are in the reactor and prevent the reactor from overheating in that sense. Pebble bed reactors are expected to be about 25% more efficient than burner reactors, which is good news for us. We can produce more energy with them. And then as far as the long-term safety, like I mentioned, the nuclear fuel is contained in graphite, which is impermeable to water. Now, all of this is really good news. It's yet to be seen whether pebble bed reactors will become widely used in this country. I believe they're being tried out in other countries, though. There are other nations that have less reluctance to nuclear fuel than the United States, and we'll discuss that a little bit more at the end of lecture. So, quick quiz question. Pebble bed reactors are considered safer than traditional reactors because of all of the following reasons, except, so you're looking for the one that's wrong. A, uranium is encased in graphite and protected from contact with water. B, the amount of uranium can be controlled very carefully so the reactor doesn't overheat. C, pebble bed reactors do not produce thermal pollution. And go ahead and think about that. Pause if you need more time. And the correct answer is C. So we're looking for the incorrect statement here. That's what all of the following except means. We're going to try and find the false statement. And pebble bed reactors do produce thermal pollution, just like every other nuclear reactor. We're still heating up a fluid, we're still boiling water, we still need to condense that water back down, condense that steam back down to liquid, and that requires cold water, which means that we're producing thermal pollution along the way. The other two statements on the page that the uranium is encased in graphite and the amount of uranium can be controlled very carefully. Those are both true statements, so C is our correct answer. All right, we're going to take a little side jaunt and discuss types of radiation because this will help you understand radiation sickness, radiation poisoning, and some of the drawbacks to nuclear fuel, which is will kind of help you understand why people don't prefer nuclear reactions in the United States at this point in time. So we have three main types of radiation. The first one is an alpha particle, which is made up of 2 protons and 2 neutrons. And this is one of the types of particles that's released when we do nuclear fission. And alpha particles are not very dangerous from the outside, meaning if you were getting bombarded with alpha particles, most of them can't make it through your skin. They're radioactive, but it's not horribly bad. However, if you swallow alpha particles or you swallow a source of alpha particles, like you swallow something radioactive that is going to be decaying over a long period of time, that can be very harmful to your cells because now you are walking around carrying a source of radiation inside you. Never a good thing. Beta particles are either electrons or positrons, which are those very, very small particles, much, much smaller than alpha particles. Now, beta particles can penetrate the skin, but they can be stopped by thick metal. So if you are working in a radioactive environment, a thick metal shield should protect you from the beta particles there. And then the final one we have here is gamma rays. Gamma rays are pure energy. Gamma rays penetrate very deeply, and they can only be stopped by very thick, heavy metal. So we want to watch out for gamma rays. Actually, you want to watch out for all of them. It's not good to be exposed to any of this radiation, but gamma rays are the ones that are potentially can penetrate the farthest. Now, some of the drawbacks of radiation, in small doses, radiation can cause mutation to DNA, which can eventually lead to cancer if you're exposed to enough of it. Now, that's in very small doses. We'll talk in a minute about what large doses can do. So here's a picture of the electromagnetic spectrum. I apologize for the pixelation on here. When we're talking about gamma rays, we're looking all the way at this end of the spectrum, which are even more intense and powerful than X-rays. So here's what we can see, this little region right here. Here's ultraviolet, there's our X-rays, there's our gamma rays right over here. And as you can see, the frequency increases here. The wavelength decreases and the frequency increases as you approach the gamma ray end. So quick quiz question, which type of radiation is the heaviest? Think about which one has the largest particle or would weigh the most if we were able to put it on a scale. Would that be A, alpha particles, B, beta particles, or C, gamma radiation? And if you haven't chosen your answer yet, go ahead and pause. The correct answer is A, alpha particles. Remember that alpha particles have 2 protons and 2 neutrons. And so they are much, much heavier than beta particles, which are only an electron. And electrons weigh a fraction of what protons and neutrons do. And then gamma radiation is actually a type of radiation. It's not really a particle with mass, although if you talk to a physics teacher, the whole energy mass thing is a little bit fluid. All right, on to half-life. Half-life, this discussion of half-life is going to help you understand why storing nuclear fuel long-term, spent nuclear fuel, is a big deal and why people are very concerned about it. So half-life, by definition, is the amount of time that it takes for the concentration of something to decrease by 1/2. So, for example, after 1 half-life, the concentration is half of the original. After 2 half-lives, it goes down to 1/4. After 3 half-lives, it goes down to 1/8, and so on. So the half-life of a particular material determines how dangerous that radioactive material is. For example, the half-life of radon-222, which is a naturally occurring radioactive gas, is 3.8 days. That means that in 3.8 days, you'll have half of the concentration left in the room or wherever. And after about a week, you'll be at 1/4 of the concentration. After 2 weeks, you'll be at 1/16 of the concentration because, 3.8 and then 3.8 again. So radon-222, although we are concerned about it, and we'll talk about it when we discuss indoor air pollution, not as big a deal as something like radioactive waste elements from a nuclear power plant. Their half-lives range from 10,000 to 2 million years. So when we're talking about something where we need to wait for it to get down to a concentration of, let's say, 1/100th of what it is initially, the half-life, if the half-life is 10,000 years, we're going to be waiting for quite a long time, because after 10,000 years, we'll be down to 1/2. Do another 10,000, we'll be down to 1/4. Up to 30,000 now, we'll be down to 1/8. We're going to be waiting for quite a long time. I mean, 10,000 years is all of recorded human history. So if we had stored something radioactive, the very first record of human history, 10,000 years ago, were we pulling it up right now out of the ground, it would still be deadly, because it would only have decayed to 1/2 of its original concentration. So the longer the half-life, the longer something needs to be isolated before it's safe. And this is where we run into problems with our spent nuclear fuel, because nobody wants to be responsible for figuring out where to store that waste. Nobody wants to have it buried near them. Nobody wants to have it stored on site at their particular plant, which is what's going on right now. So right now we're kind of in a holding pattern. We have nuclear waste. We don't know what to do with it. And in the meantime, it's actually sitting at the power plants, being stored at the power plants under high security, which some people feel is a potential terrorist threat. All right, so I told you we'd get back to radiation sickness. Now we said that short-term exposure to radiation can damage DNA, and it can cause some other minor problems. Our major concern, though, is with long-term exposure to radiation, which may come if there's an explosion or a meltdown at a power plant that will allow the radiation to vent into the environment. Explosion could come from a terrorist attack. Meltdown could come from something like the earthquake that we had in Japan recently. The earthquake in Japan a couple years ago caused the coolant pumps to fail on the nuclear power plant. And so the reactor chambers, one of the reactor chambers overheated and actually did melt down. There was a partial meltdown. They were dumping water on it from the air and were not quite, I mean, they were able to slow down the reaction for the most part, but there was still some radioactive material that vented out into the atmosphere. And there's areas in Japan where you still aren't supposed to go because of that radioactive exposure. So long-term exposure to radiation can cause a number of different things. Leukemia, which is a type of cancer of the blood, thyroid cancer, other forms of cancer, and then tissue damage. And I just want to say really quickly, some of the things like hair loss, like the things that we see people who have been undergoing radiation therapy experiencing, those are also some of the symptoms of radiation poisoning. Now, we currently use radiation as a way of combating cancer, which is a little bit ironic because radiation can also cause cancer. But the way that we do it now, it's very targeted, and it attacks just the sites where the cancer cells were, which kills off those cancer cells and helps prevent them from coming back. So, advantages of nuclear energy. Nuclear energy, first of all, is carbon-free. Once the plant is operating, we are not releasing carbon dioxide into the atmosphere. So a lot of people say hooray about that. The new technology, like we talked about, is making it safer. Pebble bed reactors are making nuclear energy safer. And it's also making it more cheaper and more energy efficient, and that would be pebble bed reactors and the breeder reactors. The chance of meltdown or explosion is actually much smaller than the public believes. We have like somewhere over 100 nuclear power plants in the United States, and we have not had a meltdown since, well, I'll talk about it, since 3 Mile Island. We also have some new technology that's making it easier to dispose of waste. So as the technology improves, people are beginning to look more and more to nuclear energy as a possible way of solving our energy problems in the future. Now, disadvantages of nuclear energy, because you knew there had to be some. The uranium mines and the mills produce radioactive material that can pollute the environment. It's supposed to be disposed of safely and securely, but we know that that doesn't always happen. And uranium-235 enrichment process, that also produces waste that needs to be disposed of. there's always the possibility of a nuclear meltdown or explosion of a reactor, or that the reactor becomes a target for terrorism. And now, even though we haven't had anything like that happen in about 30 years, it's still a possibility, and we don't want to count that out. Now, the waste heat from reactors pollutes streams and ocean. We talked about that already. The waste heat raises the temperature of the surrounding water. And there's a funny little phrase called NIMBY that you might want to remember. It stands for not in my backyard. NIMBY basically means that nobody wants to have a reactor built near them. So it's difficult to find sites for new reactors because there's huge public protest every time they try and build one. I heard a story recently about how they were looking at this one place up in Northern California as a site for a new reactor. And in order to, the environmentalist groups obviously wanted to prevent that from happening. So in order to make their case, they went to the new reactor site and they released thousands of balloons into the air. And every balloon had a little tag on it that said, if the nuclear reactor was built and had a meltdown, this balloon would be radioactive. And so it was a brilliant ploy because most of the balloons drifted into a nearby very wealthy community. And so if you can imagine, these balloons are falling from the sky with this little message saying, hey, if this reactor gets built, you could be exposed to radioactive debris in the event of an explosion or a meltdown. And so, of course, that was huge. There was huge public pressure that was put on the people in charge of building the plant to make sure that it got shut down. So that didn't happen. And that's one of the reasons that it's very difficult to see any new nuclear reactors being built. Finally, as we discussed, the highly radioactive waste must be isolated for at least 10,000 years, probably longer, and so far nobody's figured out how to do that securely. Still working on it. We might find a way. I'm not holding my breath. So, quiz question again for you. Sorry for all of the words here, but these are important that you practice. All of the following are drawbacks of nuclear energy, except A, there are very high carbon dioxide emissions once a plant is operational. B, uranium extraction and enrichment is expensive and requires a lot of energy. C, waste heat from reactors pollutes local bodies of water. D, nuclear power plants present a possible target for terrorist attacks. E, highly radioactive waste products must be isolated for 10,000 or more years. Now remember, if we see all of the following except, we are looking for a false statement, one false statement in the midst of a bunch of true statements. So go ahead and take your time, find the one you think is false, pause if you need to, and the correct answer is A. There are very high carbon dioxide emissions once a plant is operational. We know that this is false because we said that nuclear power is actually carbon-free. No carbon dioxide emissions once the plant is operational. Every other statement on here is a true statement. B, uranium extraction and enrichment is expensive and requires a lot of energy. It actually requires so much energy that we really only produce 1 joule of energy for every 1 joule consumed at this point. But we're getting better. The process is getting more efficient. And then waste heat pollutes local bodies of water. That's true. Nuclear power plants present a possible target for terrorists. That's true. Radioactive waste must be isolated for 10,000 years. Also true. More than 10,000 years, but we like to say 10,000 as sort of the baseline. All right, we're on to the final stretch here. Let's talk about some recent nuclear disasters and what they have to do with energy policy in the United States. So, 3 Mile Island, March 28th, 1979. This is the worst nuclear plant failure in U.S. history. It wasn't that bad, but it's the worst one that we have so far. No one was killed or injured. One reactor core had a partial meltdown, and this was caused by a combination of equipment failure, poor design of gauges, and human error. So all of these things together led to the partial meltdown at 3 Mile Island. And it was a combination of this accident and Chernobyl, which we're going to talk about next, that soured public opinion on nuclear power. So if you can imagine, 3 Mile Island, actually, for those of you who don't know, 3 Mile Island is located in New York, right around New York City. So if you could imagine having a nuclear power plant fail in New York City, and all the people in that region that would be exposed to radioactive waste, you can see why people might object. Now, Chernobyl was a little bit worse. It was a power plant, nuclear power plant in the former USSR, and we believe it exploded on April 26th, in 1986. So like I said, this is 7 years after Three Mile Island. So obviously we don't have a lot of information about this. The USSR at the time was still a communist country, and was not sharing secrets with the United States. So what we believe happened is that the cooling system failed due to human error. It may have also involved, same thing, faulty readings, equipment failure. We're not really sure. So the reactor overheated and exploded and spewed radioactive material into the air. Now, the reason that we even found out about it was that several days later, a nuclear power plant in northern Europe detected high levels of radiation. And they went searching all over trying to figure out what the source was because they assumed it was their own plant, only to discover that everything at their plant was fine and this radiation was blowing in from Chernobyl. So that was a bit of a shock for everybody because even after the explosion happened, nobody in the USSR said anything. Nobody admitted that it had happened. Nobody warned their neighbors. Nobody warned the people. I don't know if the people there in the region evacuated or not, but the neighboring countries had no notice of it. So a little bit scary. That's just kind of how the Soviets operated at that point in time. So the estimate is that about 16,000 people have died as a result of this explosion, mostly from cancer. Again, we don't have any actual figures because at that time the Soviets did not want to admit their mistakes. So the area around the reactor is still barren of human life, but the animals are loving it, and you can actually go and tour the Chernobyl power plant. So this was taken from their website a few years ago. The Chernobyl power plant, 23 years after the Chernobyl nuclear disaster, Solo East Travel offers an ecological tour of the power plant. And you get to see the reactor, the dead town of Pripyat, the red forest where the pine trees turned reddish brown, orange because of the radiation. Book your private tour for only $110 per person. So if you want to go see Chernobyl, there is a fantastic way to go and do it if you're ever in the area. So implications of Chernobyl and 3 Mile Island, and more recently the power plant partial meltdown at Fukuyama in Japan. The two older ones, happened at a time when nuclear energy use was actually growing in the United States. And then there was quite a bit of media coverage, public outcry afterwards that made people doubt the safety of nuclear power. So as a result, we have sort of slowed down the development of nuclear energy in the United States. Not stopped completely, and there are definitely plenty of power plants that are still in operation, but there are not a lot of new plants being built. So in the recent news, San Onofre Nuclear Generating Station, also known as SONGS, is actually going to be completely decommissioned. And this is the nuclear generating station. If you guys have driven past it, it looks like two big domes right on the ocean. It's a little bit south of us, down by Camp Pendleton. But that is being decommissioned now. They've finally decided that it's not safe to repair it or try and repair it anymore. They were having a problem with some water leaking, and the water was radioactive, so it was a little bit like there was radioactive waste leaking, but not really. It was pretty minor by comparison. But the concern was that if these sorts of things are happening, that something worse could happen in the future. So San Onofre is now being decommissioned as well. So I don't know how to make you understand this or help you understand this, but at the time that 3 Mile Island and Chernobyl happened, a lot of people in the United States felt like nuclear technology was the wave of the future. This was going to be like the oil crisis had just happened, one of the major oil crises, and nuclear power was going to be the thing that was going to get us past this problem with fossil fuels, with oil. And so to have these two explosions occur within 7 years of each other drastically changed public opinion. So much so that not completely, but we've more or less stopped building nuclear power plants. And so we have a bunch that are still in existence and still in operation. There were a few that were still being built at the time that were brought online, but the growth in nuclear power has really slowed down. And on this quiz question, you can actually, before I show you the question, I want to show you the graph. So this is from the U.S. Energy Information Administration, and it shows from 1980 to 2010 how nuclear power generation has changed. So you can see that it was still increasing. 1980, 1985 was still increasing. 1986 is when Chernobyl happened, and I think because they had reactors planned, they continued to be built and brought into operation, but then in recent years, we really have plateaued. And there hasn't been the increase in nuclear generation that we would expect to see if this trend had continued. So part of this is renewables, part of this is the oil crisis got a little bit better, so people didn't feel the need for nuclear generation, but we also have this sort of trend going on here. Now, I kind of over-explained it, which means this question is going to be very easy to you, but I want to make sure you understand this, and this question is really just to check understanding. All right, so what is the best explanation for the recent trend in nuclear electricity generation in the United States as shown in the graph? So you want to look at the graph and then choose A, B, or C as your best option here. A, nuclear generation has slowed due to a lack of uranium. B, public opposition to nuclear energy has forestalled the construction of new plants. Or C, nuclear energy is considered inefficient and scientists are no longer pursuing the technology. So go ahead and choose what you think is the best answer, and pause if you need to. The correct answer is B. Public opposition to nuclear energy has forestalled, which means prevented or slowed, the construction of new power plants. So this is where we are currently. We have yet to see if pebble bed reactors will catch on and be safe enough that people are willing to have them in their areas. To me, they seem much safer, but there are always people who object, and so we'll see if that occurs. If you have any questions, as always, let me know. Make sure you've taken very good notes. Go back and review the parts you need to, and I will see you all in class.